Hello, we are the Computational Materials group. My name is Nami,
John?
Lana.
and we're under the mentorship of Dr. Huddle. So computational materials is using computer calculations to theoretically determine material properties, which is especially useful for performing long and complex Schrodinger's equation to look for parameters like wave functions and energy states. And by running the materials under different conditions and comparing them, we can see which one is the most stable to possibly create new materials. And for us, we are looking at not so much studied compounds to see if they have a most stable state in which there are specific superconducting or magnetic properties.
And our research started with test one.
So for the first test, we tried to gather as much information as we could about these materials. So that required us to go through textbooks and read scientific review articles. So back in 1903, Friedrich Hüssler, he combined copper, manganese, and aluminum. And alone, these elements didn't have any magnetic properties. But when he actually combined them, it became a magnetic material. So from there, we decided to pick and choose elements with similar electronic properties and determine what physical properties would be produced from these compounds. So some of the properties that we're looking for are whether they're ferromagnetic, antiferromagnetic, conductors, semiconductors, or superconductors. And then the importance of this would be that we would be able to replace materials that are already being used with materials that are more abundant and maybe possibly cheaper to make. So for task 2, what we did was we built our compounds and we sent them through the Y2K software. What the software actually does is it runs it through the Schrodinger equation in order to produce data for the different types of compounds. And then that data is sent to a graphing program where we actually build the graphs and are able to analyze what the graphs are telling us. So some of the graphs were volume optimization, density states, band structure, electron density diagrams.
And some of these calculations can run for days, but once we get these graphs, which are, for example, density of states or band structure, we analyze them. And for example, over here, we can see a very large peak. That means to us that there is an instability. And we go further, run more tests, and see if this instability gets smaller or splits. If it does, that means it's a more stable state, and that's what we are looking for. If that more stable state is ferromagnetic or antiferromagnetic, or if there is any conductivity, that's what we need. This graph, band structure, it confirms certain properties. If there is a gap, that means it won't be conductive. Or in here, it tells us that there is an F electron and it has to be flat, and that's what we are looking for. This density of states graph, we can actually extract the magnetic moment of the material from it. When we integrate the top part, integrate the bottom part, and then subtract it one from another, multiply by Bohr magneton, that's going to be the magnetic moment of that material. And the importance of this research is in that if we do find, we are lucky, and if we find some interesting properties such as magnetism, we can publish a paper, and in the future, other scientists such as chemists, they can create the material, actually study and test it physically, and if they confirm these properties or disprove it, we hope they will confirm it, then these materials can be created and can be used in computers or other industries.